And next up is Clara, who is telling us about the remnant in form of magnetars.
Okay. Can you hear me okay? Okay. No, I'm fine. That's good. Okay, so hello everybody. My name is Clara Plasse, and I'm a third year PhD student at the CEA in Saclay, France. And I'm very grateful to be here today to present my work, especially in the context of the recently launched SVOM mission, as I think we have a lot of exciting things to come. So I do have the longest title in the conference, but I assure you I will not have the longest presentation. So it's late and the conference dinner is soon. So for my work, what we are trying to do is to predict the X-ray emission from the magnetar remnant of the binary neutron star mergers. And so I'd like to start with the context, if it works. Okay. So basically, the main question we are trying to answer is, are we able today to constrain the nature of binary neutron star merger remnants? And so for that, we could have two messengers, right? We could use gravitational waves or electromagnetic waves. But as Maria Gracia presented yesterday, for gravitational waves, we think we will have some evidence of the nature of the remnants in the ring-down signal of the gravitational wave. However, this signal is expected to be below our detection capabilities today, be that in frequencies or amplitude. Now, for electromagnetic wave, however, we think and we argue that we may have evidence of the formation of a magnetar in the X-rays. So these ideas come from the observation of gamma ray burst afterglows in X-rays. So what I'm showing here is what we call the canonical light curve in X-rays. So all of these different segments, we think we reasonably understand in the context of the formation of a black hole. However, sometimes we get this. And this is very interesting. So it may not seem like it, but this is a very interesting light curve for two reasons. So first, we have this plateau situation here. This means a very consistent energy injection. And then, of course, we have this sharp decrease in luminosity. And so, in fact, these two together, we cannot explain them by the formation of a black hole today. Now, for what we know about magnetars, so they have been associated with anomalous X-ray pulsars and soft gamma repeaters, definitely in 2009, if I'm correct. And since then, over 30 magnetars were identified in the galaxy. And so we know that slow rotating magnetar exists. And we propose that fast rotating magnetar also exists, that they are born in the merger of binary neutron star, and that the millisecond magnetar injects its own rotational energy into the environment, forming the plateau, causing it to slow down and then collapse into a black hole, explaining the sharp decrease in luminosity as well. So that's it for this photo. Now we're going to actually assume that this millisecond magnetar exists. We still need to answer the question, can we detect them? So one thing that is quite important to understand about this project, though, is that millisecond magnetar are far from understood. They are still neutron star after all, so that means they obey the equation of state of ultra-condensed matter that is a big unknown today. And the main implication of this is that we don't know the maximum mass of these objects, which has a big impact for us. However, their existence is not prohibited by theory. Some models even predict their birth in the merger of a binary neutron star, which is the case of the model that was developed by the modeling lab at the CEA, which, assuming some equation of state, was then able to predict the corresponding X-ray light curve of the magnetar. So this code is called GRB because it was developed by Jérôme Guillet, Raphaël Reynaud, and Matteo Bulli, who's in the back. And this is a similar picture as we have seen Phil presented a bit earlier. So the code, in fact, takes into account the geometry of observation in 3 zones. So first you have the jet zone. It's in this zone that we have seen all the GRB so far. When you move a bit away from that, you are in the free zone, where you see the magnetar almost directly interacting with the environment. And when we move a bit away again, we are in the trap zone where the emission is highly reprocessed by the magnetar, by the ejector, sorry. Oh, sorry. Be better. What you have on the right, so here on the top panel, you can see the emission from each of the zones. So in red, you have the emission from the free zone, and in blue of the trap zone. And the bottom panel is the physical origin of the emission. So you can see the dominating one is SD for the spin down emission of the magnetar. And in black, for instance, you have the radioactivity from the air processed ejecta that goes back to the value of stability by radioactivity. Okay. And so for my part in this work, I implemented so a more physically accurate model that was presented in Daniel's talk, I think yesterday. And I also linked all of the parameters to the orbital parameter of the binary star. Because yes, I came to the right conference for this, as I also developed a gravitational wave simulation for this case. So this code operates in a given observing run for LEGO, Virgo, and Cagra. And basically, the main output I'm interested in this code is that we have at the output the localization precision on the sky. And so with that, to bridge theory to observation, I have applied both of this code on the simulation of a population of binary neutron star. So the recipe for LVK is first to choose masses for each of the neutron star progenitors. Then to simulate their gravitational signal through the PyCBC, so the gravitational wave detection pipeline. And then the plan is to select the well-localized system, because for those systems, finding an electromagnetic counterpart would be feasible. And lastly, on this remaining system, I did the GRB analysis code to do prediction on the X-ray emission. So I guess the first question we need to answer is, do we actually form a magnetar? And so based on consideration of mass only, the answer is yes. We may form up to 30% depending on the equation of state. And you can see here, even on the well-localized event, you have even very little, but still some of them that may be stable. But we still need to know how to detect them. And so for that, I'd like to propose 2 detection scenarios, depending on where we are in the geometry of observation. So first, if we are in the free zone, you can see that first this concerns a smaller number of systems, as the solid angle is smaller. But since the emission is less reprocessed, we expect a much higher luminosity in this zone. But also a shorter duration emission. So for that, we would like to propose a detection with wide field of view instruments, such as the FXT aboard the Agitad probe. And for that, my simulation indicates that the mean flux may be within the detection capabilities. Now for the trap zone, so we have more event in this configuration. We have a lower luminosity, but however, since the radiation is reprocessed, that means that we have a longer duration emission, which may even last after the magnetar has collapsed into a black hole. And this is very interesting for us because usually the time is the most sensitive parameter for this study. And so for that, to detect them, we need a precise detection strategy. So with a smaller field of view, which also means more sensitive instruments that would quantile the gravitational wave error box. That might be a jump for MXT. And so with that, I just wanted to show that, in fact, the result on the simulated population of neutron star the possibilities are pretty much endless. I have a lot of free parameters after all. This kind of plot were shown by Susanna and also Lorenzo. This is my take on that, actually. It's so the distribution of precision of localization depending on the distance. So it's always nice to see and also to check the simulation. This plot is the distribution of flux depending on the equation of state, predicted flux for the magnetar. And then this plot is is one where I played with the with the magnetic field, interesting magnetic field of the magnetar. Again, depending on the equation of state in increasing predicted maximum mass. And the impact, so this shows the impact on the detection possibilities. Okay, so then last year we'll just go quickly over observation strategies with SVOM specifically. But this is mostly an excuse to give you news about SVOM, honestly. I will just quickly harass you one last time about SVOM, but I think you get the drill by now. We have seen it multiple times. So about SVOM, you have 4 main instruments with 2 wide field of views that are Eclair and GRM that look at the sky at all time waiting for an alert. And then if you have an alert, the platform Toulouse to align the smaller field of view that are the X-ray telescope MXT, as well as the visible telescope VT, to do an effective follow-up. And then also for the follow-up, we have a synergy with ground telescopes that are interconnected. And SVOM was successfully launched on the 22nd of June. And so other than GRB alerts, we have another possibility of observation, which is in the case of gravitational wave alerts from a binary neutron star merger. MXT will come pave the gravitational wave error box to find the remnants. And who knows, maybe one day we'll have an interesting light curve. And I would just like to finish with an interesting case. Well, it's not the most scientifically rich, but it's one I found very exciting. So this is what you get. So what you see here is what we call the South Atlantic anomaly. And it's a non-radiation hazard for space mission. And so when we cross here, all instruments, at least MXT, is completely turned off, and the shutter is closed to avoid radiation damage. For this observation that you see here, I hope you see it, by the way. I think Eclair got the alert when we were about here, a few minutes before entering the South Atlantic anomaly. The platform still slewed, and we were on target 6 seconds before entering the South Atlantic anomaly. And this is the 6-second observation. So here you have 150 photons, more or less, right before shutting off. And what you have here is you can kind of guess the cross-shaped PSF from the MXT instruments. At least MXT guessed this and was able to refine the localization with this. And I think with this one, if I'm not mistaken, we ended up with 20 arc-second localization from the finite localization. So we are doing pretty good. And with that, I will just bring my conclusion. So in this presentation, I raised the question of the nature of the GRB's central engine. Specifically, we are still wondering if we always have a black hole or if we could have a neutron star. So in my project, we simulate a magnetar central engine to predict the X-ray emission. And so we thought that, so I went over that briefly, but it would be a very rare event, but the detection today is still possible. So we would like to point out that it's important to organize follow-ups now as well as for later detection capabilities. And for that, SVOM is also designed to unveil the nature of GRB central engine. And this is especially important because a single detection would be important for GRB physics as well as merger physics. And also, I didn't put it there, but also to have a constraint on the equation of mass. Thank you.
Questions?
Thank you very much. It's very interesting. So I'm just curious, I'm thinking aloud here, so this might be nonsense, but so obviously you're looking at, you're thinking about the cases where we're potentially triggering on a GRB, is that right? But because there's a much wider angle where you can see this emission that you're simulating from, is the expected rate enough that we should be looking in like the ACME catalogs or the SWIFT catalogs or whatever to see if we've actually just, without seeing it on axis, there was no gamma ray burst trigger. If there are these things around, can we place limits on them or expect to find them in the catalogs, or will they just be too faint to really distinguish as interesting?
That's a really great question, actually. And I've been thinking that also for Einstein probe FXT, because we've been seeing a lot of new kind of transients.
Yeah.
And so one could wonder if, this could be linked to something like this. But then honestly, so I went very quickly over this, but the main thing I wanted to stress on this slide, and I completely forgot, is that, the amount of detectable millisecond magnetar is expected to be very low, even with more conservative equation of states. So my answer is a bit vague, but I would say it is definitely possible, and it would be interesting to link it to that, but keeping in mind that we expect the rate to be very low.
So I guess it partly comes down to what fraction of neutron star mergers result in GRBs that we see, because we don't know the jet angle. So how many of them are there that could be out there, which we don't really know? So
right, absolutely, yeah, because the answer to that will also be a lot more than in the jet. So
sure.
Yeah,
but it might perfectly balance that 1% or something. I mean, who knows? So yeah,
that is a valid remark here.
Are there other questions?
Yeah, just a simple question. When you say when you're looking at it when you're in a situation you're viewing from the side and it's in the trapped region zone, what do you mean by reprocess? Does this emission, do you expect it to change, peak in lower energies, or just take longer, or?
Right, thank you. So yes, absolutely. So this is what you can see here. Actually, you might see it better on the other one. So basically, that means that the opacity is much greater. You also have a big impact on the electron diffraction that was mentioned by Phil talks earlier. And so that means that this all depends on the opacity, which is a case-by-case thing. But typically, what you would have is that the emission, first, you inject the same emission as the spin down. It's exactly the same emission. But it doesn't come through directly, and it gets trapped in this ejector. And then you have to wait for the ejector to cool it, to expand, for it to be able to pass right through. And then sometimes the ejector would be heated, and so you also have the emission lasting longer. And so this is kind of what you see here is what I mentioned a bit later in the talk. Typically here is a great case where you have the trapped emission that lasts longer than the free emission.
I don't see other questions, so thank you very much.